All right, so today we're going to cover the metric system, and the first thing that I want to do is contrast U.S. customary units versus the metric system. Okay, U.S. customary versus the metric system. And last time we talked about the English system or the U.S. customary system, which has its roots in the English language, has its roots in words like inches, yards, miles, foot, which are rather arbitrary. So the U.S. standard units, also called the U.S. customary units, it kind of depends. So American standard units would be another name for this system. The metric system. Another name for the metric system is the SI units, or SI units. SI stands for International Standard, except it's in French, so it actually is backwards for us in English. Standard International is why it's SI. So we have a contrast here between the American Standard units and the International Standard units, or the U.S. customary units versus the metric system. So I want to do a contrast here. First of all, I want to say that the U.S. customary system was arbitrarily derived, whereas the metric system is more mathematically derived. Arbitrary and let's just do mathematical. It looks weird too. What's missing? An E between. Okay, let's get this going here. Mathematical. There we go. Maybe I should stop lambasting English. All right, so, but the whole point here, and we said this last time, that the English system is very what? Clumsy. So I want you to think of that word. It's very clumsy, and that's because it was arbitrarily derived. We'd have to do a study, a history study, in order to figure out where did the word inch come from. In our common everyday usage and in our common everyday knowledge, what is an inch? Well, we know what an inch is because we use it for measurements, but where did it come from? Where did it get its name? Probably an interesting history lesson, but as far as mathematics is concerned, it's very arbitrarily derived. Then the next point is that the metric system is standard and the English system is not standard. Say, well, but it says standard here. Well, each individual unit has been defined and standardized so that a foot is a foot is a foot, an inch is an inch is an inch. But what I mean by standardized is there's no rhyme or reason or relationship between the numbers. Think about the U.S. customary units of length. We've got the number 12 inches in a foot. Then we have the number 3 feet in a yard. Then we have 5,280 feet in a mile. What's the relationship between their numbers? Well, there isn't one. All right. The U.S. customary units of capacity, the ounce. Oh, and we even have the same name for two different things. The fluid ounce, and which is a capacity, and ounce, which is weight. So an area of confusion. So we don't have standardized numbers in that there is no relationship between the conversion facts. So that tells us that the conversion facts have to be, number 3, memorized. Okay, so if we're doing the U.S. customary systems, they're very arbitrary. Look, if you just even look at the words, inch, mile, cup, quart, pint, peck, all kinds of confusion. Ounce. Okay? The metric system was mathematically derived based on what? place value. Okay? Yes, we do have prefixes, and yes, they have to be memorized, but they're standardized throughout the metric system. So this is not, there's no relationship between the units. Those units have to be memorized. Here, the metric system really is standardized, isn't it? The metric system really is standardized. It's set up on place value. It's on the same setup as place value. It is base 10. So it's very standardized. Yes, we memorize our prefixes, but those prefixes correspond to place value, don't they? Kilo corresponds to the thousands place, hecto to the hundreds place, etc. The U.S. customary system, they're only standardized individually. There's not a nice relationship between all the units, as is the case with the metric system. The metric system is standardized as a whole. It's an entire system. The U.S. customary units are not a system per se, are they? They're only standardized as individual units. And what I mean by that is that there is a standard inch that all inches are supposed to conform to. There is a standard foot that all feet are supposed to conform to. But there is no standardization between the units. That's another reason why the English system is so clumsy. Okay, so third idea here is because there's no rhyme or reason to the individual units, there's no relationship. Okay, that's kind of what I should probably say. No relationship. No standard relationship between the units. And because of that, what do we have to do? We have to memorize the relationships. Do we not? And we spend a lot of our elementary math time learning this clumsy system. I would be all for converting the United States to the metric system. Okay? You know how much time that would save us? There was a movement in the, I think, early 70s to do so, and people were all up in arms. Okay? And I understand the idea of being separate, and historically and politically, would be a separatist. Let's let the United States take care of itself. You know, I don't know, trying to dig out of my brain. What was that called? The Monroe Doctrine or something? Yes. So, okay. I am for national autonomy, and I think we're getting more and more away from that, and we're becoming so global. But the U.S. customary units is an example of something that's very awkward to use, okay? And I would be all for eliminating it entirely. It would save us a whole lot of time. It would take a big chunk out of elementary arithmetic. All right, so, and because these units have to be memorized, what do we think about memorization in math class? We don't want it, do we? Memorization is what? It's a poor learning tool, which makes it a bad teaching technique. Okay? It is necessary here, though. And once we drill, and we have enough stuff to drill and memorize, we don't need to have to learn all this measurement stuff. Okay? So the U.S. customary system or the American standard units is not very standard at all. It's very clumsy. We have to memorize the relationships. That's not the case here. It's necessary only for the prefixes. So, 1F or 2 on prefix? 1? Thought that looked odd too. Today's going to be a bad spelling day. You only have to memorize the set of prefixes. But the prefixes are standard for all 3 types of measurements. We have units of length, units of capacity, and units of weight. And we learn the system. We don't memorize arbitrary units. So we're really not memorizing in the same sense. Here we have to memorize all these relationships between these arbitrary units and arbitrary numbers that have to be use rote memory on. Here, we're not really memorization. No memorization needed. We learn the system, understand the system, and we're done. So the metric system is superior to the American Standard or U.S. customary units. So the metric system is scientific and mathematical. It is standardized. Really no memorization required. And the fourth idea is that the U.S. customary system cannot be expanded. And in the metric system, or the standard, international standard system, we've expanded it a lot. Let's go back here. Smaller than an inch. What's smaller than an inch? Anybody tell me? A fraction of an inch. Okay, right? Can we go any smaller than that? Do we need to go smaller than that? Sure. What's an inch? About that big? There's a whole lot of units, or a whole lot of units below that in the metric system. So what happens is we go smaller. We get micro. We just add a prefix. It's easy to expand the metric system to very tiny measurements and extremely large measurements by adding prefixes. Because how far does place value go? It keeps going and going and going, even though we may not know the names as we keep going and going and going. So we have micro. Micro is 1/1,000,000th of a meter. And then we kind of skip every 1,000. We don't go to, the next prefix is, anybody know the next prefix? No, we're going smaller. Micro, nano. Nano, we're going to skip to the next, we're going to go by it, we're going to go 1,000 times. So we're going to go billionth, 1/10000000th. It goes all the way down to unpronounceables, okay? A nano is a billionth. Does anybody know what a trillionth is? Without Googling it real fast on your computer, it is pico. So you get the idea here. Are you getting the idea? This is scientific, it's mathematical, it's standard, it makes sense, we can expand it. We don't have to really memorize it. We learn the system, yes. I suppose you'd have to memorize somewhat the prefixes. But we can easily expand it. On the other hand, what's larger than a mile? Or if we're doing things that are very large and very small. There's nothing larger than a mile, there's nothing smaller than an inch. What's larger, or what's smaller than a millimeter? Micrometer. What's smaller? Let's go with bigger now. What's bigger than a kilometer? Anybody know? Kilo is 1,000. Million is, you should know this one. Pardon me? No, that's billion. There's one in between. Tera's trillion. Mega. Computer-wise, we should know this. Megabyte. Right? Megabyte, gigabyte, and now everything's in terabytes. So we're easy to expand. A millionth, a million, or bigger, a million meters is a megameter. A billion is, so we got mega, then we have giga, and then we have tera. If you think about your computer, nobody does a kilobyte, I guess. I don't know, but megabyte is common. Gigabyte, I don't know, I'm not a computer geek, but I do have an external hard drive, and it is a terabyte of storage. Okay, so that's 1 trillion bits of information, whatever. Okay, so the next thing we can compare, the English system or the U.S. standard units, U.S. customary units, cannot really be expanded. We'd have to invent an entire new unit, give it a name, and decide how many miles would be in it or whatever. So we can easily expand, because this is all place value based, we can easily expand it. We don't really have to memorize it. This is arbitrary and clumsy. This is scientific and mathematical. Okay? Science class does not use the U.S. customary units, does it? Why not? Because it's arbitrary, and because it's clumsy, and because it has to be memorized, and because it can't be expanded as science technology increases. So the next way we can compare it, number 5, the next way we'll compare it is the computation. This is clumsy in computation. We have to literally do quite a bit of division and quite a bit of multiplication when we're interconverting. So the U.S. customary system requires computation to convert units. Okay, it's clumsy. You have to actually divide things out. You have to actually multiply things. What about here? If we taught our students the metric system in an efficient manner, they would hate having to go back to the U.S. customary units. Why? No computation. What do? Move the decimal. We're multiplying and dividing by powers of 10, right? So all we do is move the decimal. We do not actually do any computation. We're just going to move the decimal. No computation. Which brings me to the next thing. The computation here is fraction-based. We're going to do fraction multiplication. We're going to express our remainder as a fraction. We're going to use mixed numbers. We have to. If we're going to be accurate in the U.S. customary units, we have to use fraction math because the units are so incompatible. Once we start getting into decimals, we'll have to do rounding and so forth. So that's why we need to use fraction math, and make sure when you do any U.S. customary unit problems for me on tests, quizzes, homework, whatever, make sure your remainder is expressed as a fraction. Do not round. Because if we don't, otherwise we do too much rounding. And what happens when you round? It becomes more and more of an estimate, less and less of the actual answer. Over here, decimal math. So think about it for a second. Most students would rather do decimal math instead of fraction math, right? Think about yourself. Most of us would like just moving the decimal point, not actually multiplying and actually dividing. So the U.S. customary system is clumsy in all aspects. Too many things to memorize, too much computation, too many remainders, and so forth. So the last thing to bring up about the U.S. customary versus metric is the idea of compounds. There are no metric compounds. Because the units are standard, because there's a standard place value between them, no metric compounds. One of my biggest problems with the Abeka arithmetic is how they handle the metric system. They sprinkle the metric system in with the U.S. system, and they do metric compounds. Metric compounds are not correct. What do? We put them in decimal form of the larger unit. No metric compounds. If you see, I shouldn't say if, when you see what looks to be a metric compound on a quiz or test or homework, you don't ever do metric compounds. They don't exist. I don't know why they get thrown into arithmetic textbooks. If I have 3 kilometers and 17 centimeters, what in the world? I'm only forced to use compounds in the U.S. customary system. I have to do, let's say, 4 feet, 11 inches. Or I have to go to a mixed number. What about that? That's because the U.S. customary system is what? Clumsy, arbitrary, and should be eliminated. What's this? This is actually just as wrong. We always go to decimal math. Oops. Kilometer and centimeter? That's not what I meant to do. I meant to do 3 meters. So that would be 3.17 meters. You do not want to do centimeters and kilometers. It would be, what? 3 point, oops, we'd need that extra 3 in there. That's kind of ridiculous. So no metric compounds. We would never write 3 meters, 17 centimeters. We write it as a mixed decimal in the larger unit. Okay, so that's another thing. We have to deal with compounds. What did we do last class period at the end? We had to review how to add, subtract, multiply, and divide compound measurements. Is that the case here? No, it's decimal math only. So I don't see why we don't like the metric system. Decimal math only, no memorization, no actual multiplication and division. The metric system is so much better than the U.S. system. So, can you contrast the two? Metric, scientifically and mathematically derived, what's it based on? Place value. All right, the U.S. system, what is it? Arbitrary. It's based on English words from whenever. We'd have to do a historical study to figure out the roots of each of those units, wouldn't we? All right, then the metric system is completely standardized. All the same system. We have our 3 base units, don't we? Meter, liter, gram, and then we can expand on them indefinitely, larger and larger, using different prefixes, going through place value. We can expand on it indefinitely, almost going smaller. By the way, if you were to look up the SI units, we can go all the way up to a septillion, which is, you've got million, billion, trillion, quadrillion, and then septillion. That's 7. So there's all those places all the way between. What would 5 be? Quintillion, hexillion, septillion. So how many decimal places is that? That, by the way, is called a iota, okay? And then we can go all the way down even beyond pico into all these very, very small units. Even in physical science at high school level, we do get well beyond kilo, use mega and giga a lot, and so forth. So it's completely clumsy, scientific. So the last thing in the comparison is I want you to understand that the international standard units are all based on the metric system. Standard international, or international standard, units is synonymous with the metric system. And in arithmetic, we deal with 3 base units, don't we? We deal with the meter, the liter, and the gram. All correspond to the ones place, because it's place value derived. But guess what? We can use all kinds of things. Okay? The base unit of time is second. You've heard of a nanosecond, have you not? What's a nanosecond then? Well, if you know that nano is a billion, then you know billionth, then you know that a nanosecond is 1 billionth of a second. SI units, there is a little bit of a difference here. In the SI units, gram is too small. So actually, kilogram is the standard unit used in science. So whenever you're doing physical science computations involving weight, remember we did foot-pounds last time dealing with work? Kilogram meters is comparable to foot-pounds. Gram is too small. But other than that, it's going to be the same. And in fact, you've probably seen this one. What is that? That's the SI standard unit of amount of substance. Usually coming from the idea of molecule, I believe. You've got molecule, how many molecules or how many atoms are present. So it's not a weight measurement, it's an amount of substance. Electric current uses the ampere as the base. So we can do all of these, then we can add our prefixes to. We're still using gram, but when we're doing physical science computations, we have to go to kilogram, but the prefixes still apply. What's a megagram? What's a gigagram? Okay, I don't think we'd be using those, but we could if we needed to. Kelvin is the thermodynamic SI unit of temperature. And then there is a light intensity unit called the candela, from the word candle. Kind of interesting. And then Kelvin is in the degrees. You're familiar with Lord Kelvin and absolute zero. Though most of the time, that's for thermodynamic temperature. Most of the time we deal with Celsius. Don't forget temperature. We don't really do temperature conversions much in arithmetic, even at junior high level. Why do we use Celsius temperatures in science? Kelvin's kind of extreme, but your high-tech physics involves Kelvin. Why do we use Celsius instead of, what's the US customary? Fahrenheit. Why do we use Celsius in science and not Fahrenheit? Same reason. Fahrenheit's degrees are not standard. Why is Celsius, what's the other name for Celsius? Does anybody remember? Its old name. The one that I learned in grade school, but you did not. Centigrade. Why is Celsius and centigrade the same temperature scale? Because each degree is based on 100. The earmarks of temperature in science class have always involved water, kind of as a standard substance. All right, what's a calorie? It's the amount of heat needed to raise 1 gram of what? Water, 1 degree Celsius. Okay? So everything involves, as far as standardized relationships, involves water. So what's the boiling point of water Fahrenheit? 212, right? What's the freezing point of water Fahrenheit? Those things have to be what? Memorized. What's the freezing point of water Celsius? 0. What's the boiling point of water Celsius? 100. Do you see how it's standardized, that there's exactly 100 degrees between The freezing point of our standard substance water and the boiling point of our standard substance water. All right, so can you contrast the metric system versus the English system? So as an elementary teacher, what do you need to concentrate on when you're teaching measurements? Yes, we use the English system in everyday life, but what is used in science where it really matters? Metric is. So we need to have a goal. We'll talk about teaching intermediate measurements in another class period, but we need to be making our students comfortable with the metric system and making our students like the metric system. They should already. I erased it. But what did we say about the metric system? No computation, no memorization, no fractions, yay, no compounds. So we need to be, I'm promoting the metric system today, can you tell? So what do you need to do for your students? Get them comfortable with the metric system and show them how easy it is. They don't have to do any actual multiplication. All right, we're dealing with miles. What's the number there? 5,280. So we have to multiply with it, right? Or divide with it. Yuck. You want to do a division problem with the divisor being 5,280? Not me. Give me kilometers any day when I can just move the decimal. Why do students not like the metric system? They don't understand it. They think it's hard. And it is because it is unfamiliar, right? So if you took a lot of science and you liked science and you were good at science, you probably like the metric system. But if you're afraid of science or never really understood how the metric system works, then it becomes difficult. So what we're going to do next is go through the metric system and using the metric system and converting into and out of the metric system eventually. We do have to be able to do some metric English conversions. You will have to do some metric English conversions. So let's go through the metric system and let's talk about the system itself. It is a very standardized system and it is on base 10. That means each prefix, each level of our unit is a power of 10, with the base unit, the foundational unit being the ones place. Okay, and several of you on your visuals, you made that stair-step thing, which is one way to help students be familiar with moving the decimal one place each unit, and then the conundrum comes with which way do I move it? Okay, but once you know have the overall system in your mind, metric conversions are easy. It'll take you a fraction of the time to do chapter 9 than it did for you to do chapter 8, unless you don't understand the system and you're moving things the wrong way or the incorrect number of places. So the first thing we have to do is understand how the metric system was set up. The metric system was set up to mimic the place value system. The metric system was set up so that each unit, as we get larger units and therefore smaller numbers, will be 10 times bigger, just like place value. The ones place goes to the tens place. It's 10 times bigger, okay? And then the hundreds place, next one up, is 10 times bigger than the tens place. So all we need to do is when we are teaching the metric system, we need to do it completely separate from the U.S. customary system. Do not teach them at the same time. We're going to need to divorce them. They are completely incompatible with each other. And you will find when you do metric to English conversions, it's always going to be approximate. Because the conversion fact has been rounded, hasn't it? Is there exactly 2.54 centimeters in 1 inch? That's an approximation. So we're losing accuracy not only in our own computation, but there's a lack of accuracy even in the conversion fact. It's not exactly 2.54 centimeters to make 1 inch. That's rounded. It's actually an estimate. It's a very good estimate, but it's not exact. So the two are incompatible. They barely interconvert between the two, and that causes some very severe problems in in industry and in technology, because that's why we have to completely get rid of all the English measurements and do everything in metric, because they're incompatible. And when you're talking technology and industry where little bits make a big difference, you cannot use the English system or the U.S. customary system. All right, so we need to understand how the system works. And first of all, we need to relate it to place value. That's how it was derived, and that needs to be how it's used. That's why you do not teach English and metric together in 6th grade. You say, well, we're in the measurement units. That's because they're completely different in how they're set up, and they're completely different in how they work. Otherwise, you're going to cause confusion. We do need to bring them together at the end, but we want to do the metric system by itself. Its computation is different, its setup is different, it's a different thing altogether. Then after we get the metric system down, and we should already have the U.S. customary system down, then we will say, okay, here's how you convert the two, and it's always going to be messy, and sometimes the answers will be slightly different between two students because one used a certain conversion fact and divided, and the other used the other conversion fact and multiply, and their decimal is going to be a little bit different. Okay, so it's incompatible. Do not teach them together. If my curriculum did, I would cross off those problems out of the homework and tell them to not do the metric problems. Okay, literally. Say, we're going to only do the U.S. customary units. If there's a kilometer problem in your homework, skip it. I don't want to mix the two up at all. Otherwise, that just perpetuates this confusion about the metric system. When the metric system is easy and the U.S. system is hard. But for our students, the U.S. system is familiar and used and practiced a lot before they get to the metric system. So, base 10, we have our base unit, which can be meter, liter, or gram. And teach your students to use cursive handwriting when they write the units. Don't print. Why? Well, that's such a problem that nowadays liter is always capital L, never little l. It's too much of a confusion. Even when we're writing milliliter, it sometimes will appear like this, but even more and more we're using that. So capital L for liter is now the standard way to abbreviate it. Okay? Because too many people cannot tell, and when things are printed, can you tell the difference between 1 and L, and lowercase l on a computer? Printout, can you? I can't. Okay? Is it exactly the same? I think it is. Anyway, so we've got to get the place value system figured out. So we do have our meter, liter, and gram as our base units, and that is the ones place. Then if we have a longer measurement or a larger quantity, we are going to use deca, then hecto, then kilo, which is fine for elementary and junior high level arithmetic. We don't do mega and giga and tera. But if we understand the system, we can easily expand it in high school physical science and high school physics. Okay, in teaching 10th grade physical science last year, I had all kinds of problems with the metric system. And so the decimal was frequently out of place in answers because they couldn't convert back and forth. All right, because we had to do some things with chemistry, you have to do some larger numbers or smaller numbers or what have you. So we need to get the system down so we can expand it for science class. These two are not really used in science class. As a matter of fact, when we expanded it, did we learn a prefix for 10 million, 100 million? No, we did. Mega is a million, and we skipped all the way to giga, a billion. That's because these middle ones really are not practical sizes, especially not in the United States. All right, so these are place fillers. But they have to be here because we have to have all the digits present in our place value system. So this is the tens place. This one's not used at all really much in science. We might see it from time to time. We do have to work with it in arithmetic. This is the hundreds place. And this is the thousands place. When I teach the metric system, I never write ones, tens, hundreds, thousands. I never write it like that. I always write it ones place, tens place, hundreds place, thousands place. So kilo means 1,000, yes. But when we're using it as place value, we need to say that kilometer is in the thousands place. Kilogram is in the thousands place. We want to tether it to place value. We do not want to tether it to English or U.S. customary mathematics. U.S. customary, we memorize the number 12 because there's 12 inches in a foot. And there's no confusion there, and there's no in-between units and so forth. So that's how the U.S. customary system works. When we're working with inches to feet, we use 12. We divide by 12 to convert 2 feet. We multiply by 12 to convert 2 inches. But we can't propagate the idea that kilo is 1,000. Because do we always convert between meter and kilometer? No. Sometimes we have to convert between decameter and kilometer, and we have to use it as place, not memorization of a conversion fact like we do in the U.S. customary system. Do you understand what I just said? I've had students that anytime they do a conversion in the metric system with the word kilo, with the prefix kilo, they use the number 1,000. Is that going to work between here and here? No, they're doing it in the same way that they did feet to inches. Always use 12. Well, anytime we see kilo in our measurement problem, are we always going to use 1,000? No, we have to put it in context of place value. So you want to teach your metric system as ones place, tens place, hundreds place, and you want to teach them that this is 10 to the 0 power. This is 10 to the first power, 10 squared, 10 cubed, right? Because then as we get bigger to mega, what is mega? Million, that's 10 to the 6th. Then we have giga, which is 10 to the 9th billion. And then we have tera, which is trillion, 10 to the 12. So the decimal and we want the decimal, the exponent, and then the prefix to all fit together. Not so much the number, okay? Because we have to do a lot of this in science class. Okay, you said, well, my students aren't going to be scientists. No, but they have to get a high school diploma, right? So we want to base our metric system and our understanding of it on the place value system. Then when we get below 1, here's our base unit for meter, liter, gram. Below the ones place, we have negative exponents, don't we? This is deci, centa, and milli. This is the tenths place. This is the hundredths place. Okay, so this is tenths, this is hundredths. Maybe we might want to get rid of those because we want to keep it in terms of decimals. Okay? Thousandth. Right? 2 places behind, -2 exponent. 1 place behind, -1 exponent. Right? We want to start teaching them the metric system the right way, the place value way, the decimal way, not anything like the U.S. customary units. That's why they shouldn't be in the same lesson. Okay? Because they're incompatible. They're not, it doesn't work that way. So we need to learn to convert between the two. We need to understand the prefixes. Kilo, hecto, deca, base unit, deci, centa, milli. We don't need to expand. We don't need to go to micro, nano, and pico, but we could when we need it. This also helps them work with terms of scientific notation. We've got to learn and teach them how to use the place value system. Then they can use the metric system and expand the metric system. Keep in mind, these are kind of placeholders. We're not going to deal with them, but we still have to, we will convert in between them. Deca is pretty much a placeholder. All right, so think about meters. What's a hectometer, hectometer? How do you pronounce that? I don't know. Never use it. Never heard it used. Decameter, never used it. Decimeter, never used it. Practically speaking, everyday life, we use kilometer, meter, centimeter, millimeter, and then micrometer. Not so much. Okay? What about liters? What's a hectoliter? We use a kiloliter, though, is really too big. It's not used. A kiloliter is about 250 gallons. So we mostly use liter and decaliter. All right, but even not decaliter. What's a deciliter? Centiliter? Not so much. Basically, you have to understand that kilometer, meter, centimeter, millimeter are your practical units of length. Kiloliter, oh, it's too big. Hectoliter, decaliter would be abbreviated like this, DA, deca, to distinguish between deca, which is just a D. Decaliter, somewhat, pretty much only this guy. Centiliter, deciliter, milliliter. Pretty much, practically speaking, we're only going to use liter and deciliter. And not deciliter, milliliter. Centiliter, no. In fact, this guy we need to talk about for a minute. Confusion does occur, unfortunately, in the metric system. 1 milliliter is equal to 1 cubic centimeter, and often dosage in medicine will be in cubic centimeters. You might have heard it called a cc. That's because if we had a little box, this is too big, by the way, but if we had a box that was 1 milliliter, a cube, 1 milliliter by 1 milliliter by 1 milliliter. I'm sorry, I said that backwards. 1 centimeter by 1 centimeter by 1 centimeter. The volume of this little cube would be 1 cubic centimeter, right? Guess how much water fits in there? 1 milliliter. So those two are interchanged frequently. So you see cubic centimeter and milliliter, they are interchanged because a cubic centimeter of volume does hold a milliliter of water, and I'm sure it's at a standard temperature and standard pressure and all this other stuff. So they are interchanged, and just, I don't know why, but this one is used more than milliliter. Okay, so make sure you get that little quirk. The book you'll have to deal with it in the textbook. All right, so what about when we're dealing with, we've got length, capacity, weight. Kilogram, decagram, hectogram. I have seen decagram a little bit because gram is so small. And remember, gram is so small that this guy is the base unit for science purposes. Then we have gram, decigram, centigrams, maybe, but milligram. So we're mostly dealing with, and especially that guy. With this is the main unit. In fact, that's the SI base unit for length is meter. The SI base unit for science class for weight is kilogram and liter. Even when we're doing speed and distance computations in physical science, we still use the meter. Okay, not the mile. Obviously that's English, not the kilometer. Okay, so do you understand how this works? The main units involved in length are kilometer, meter, and millimeter. Centimeter, some also for inch. Let me get rid of this because that doesn't fit what I've got displayed here. We'll put it down here. That is interchanged. So meter is the base unit for science and it's the base unit for math. Kilometer for distances comparable to mile. Centimeter for distances where you would use inch. Millimeter when it's less than an inch or just a few centimeters. Then in capacity, base unit is the liter. Okay. Many times in science, the milliliter will also be involved, but deciliter, centiliter, no. No. Those are place fillers. Here, hecto is almost always a place filler. It's an odd size, but it's necessary to keep the place value system intact, even though we don't have much use for it in everyday life. Deci, same thing. All right, so we need to have an understanding of how the system was set up by place value, an understanding of what units are used, and then an understanding of how to convert. Okay, if you're familiar enough with how it's set up, you don't need any crutches. But will students need crutches? Will they? And that's where your visuals, several of you that made, will come in handy. Probably the best is the stair step. But what you've got to do is you've got to think. The larger the unit, the smaller the number. Okay, if you just think about the US system, from here to here across the front of the room is what? 15 feet, maybe 20? How many inches would that be? a whole lot more, right? So what happens when we convert to a larger unit? We need fewer in number. So we are always going to divide by 10 as we go up unit by unit. The stair step helps, I think, because if we just do part of the stairs to begin with, we have the base unit, then we have deca, then we have hecto, then we have kilo. That'll help them to do it one place at a time. So that's why the stair step is superior. But by this stage, you ought to be able to do the metric conversions completely in your mind. And you think of the setup, and so when I am converting up to a larger unit, it requires a smaller and smaller number. As I go down to a smaller unit, it will use more and more quantity, more and more numbers. So that's why as we go up, we divide. As we go down, we multiply by 10. And the stair step will help us to do one place at a time. So I'm going to the left so that I get smaller and smaller. All right? And then I go to the right to get larger and larger. So what you're going to need to do is work on chapter 9. You will do 9.1 through 9.5 even. So practice moving the decimal point. Hopefully you can do it off the top of your head, but we will come back to the crutches when we talk about teaching it. But just think about it. If you have to do a metric to metric conversion, you just need to know the places. And if you know the places as well as you know the place value place names, it's not a big deal. Even if I do 15 hectometers, how many centimeters is that? That is an oddball conversion that you would probably never do in real life. But it makes sure that you can convert. What's happening? There's going to be a whole lot more centimeters needed to represent the same distance in hectometers, hectometers. So how many places am I going? 1. Decameter has the A. 2 meter. So I'm going 1 place, 2 place, 3 places would get me to deci, and then 4 places will get me to centa. So I'm converting down 1, 2, 3, 4 units. I'm moving the decimal 4 places to the right because I'm multiplying by a power of 10. I go to the right. So it doesn't matter where the conversions are. Okay? We'll see you.